Good morning, boys. I hope you're well. Apologies I'm not there today. I'm not feeling well. Hopefully I'll be back there tomorrow or the very latest on Thursday, of course, for our third lesson. Today, hopefully we're looking at our last lesson on quadratics, where we're looking at optimization. Now, it's a pretty straightforward lesson, so I won't spend too much time going through it with you. Very basically, we've been looking at these quadratic functions. I'm going to look at a positive definite function like this, where a is greater than 0. So y equals ax squared plus bx plus c. Of course, this could be in vertex form or intercepts form, although there are no intercepts for this actual graph. So optimization, we like to optimize things. We like to make them the biggest they can be or the smallest they can be for different reasons, of course. Now, let's say, for example, we're looking at the volume versus the cost of something. So we might be trying to minimize the cost when you're looking at creating a volume of a container ship, for example. All right. So obviously in this case, you can see very clearly with a positive definite, or not just positive definite, but a positive parabola, we can see that creates this minimum value. Now, we've said before, we call this a global minimum, but of course, you don't have to have a global minimum, okay, but certainly we have one here. Now, this is a minimum, so this function can represent something to minimize a particular scenario, so in this case, cost. Now, obviously, what do we know about that point there, where that turning point is? We know that it is a vertex. We can use that word, of course. It's a minimum vertex. I'm going to say minimum turning point. And so there are a number of ways, of course, that we could find that particular point. Now, obviously, one of the ways that we would often do that would be where we would look at the intercepts and then add them together and divide by 2, because, of course, it would be the midpoint of those two intercepts. But in this particular instance, this would be quite challenging because there are no x-intercepts, that discriminant is less than 0. So how else do we find that turning point? Well, of course, that turning point sits on the axis of symmetry. We also know the axis of symmetry is given by the formula negative b over 2a. So we can find that x value by using negative b over 2a for whatever our function might be, as long as it is in general form, of course. And then once we have that value, we can sub it back in to the actual equation to find the y value. Now, that's, of course, if we have a positive definite sort of function like that. Now, we could have a function that looks almost the same, but it could be some type of negative as such, where we could be trying to maximize something. So we might want to maximize volume for cost. Okay, we want to have the biggest amount of volume we can for the cost we have, or the volume versus the surface area, right? So you want to have the biggest possible volume you can possibly have. Same situation, we simply need to find that turning point or that vertex. We can do that by either finding the axis of symmetry. Okay, that's our line there. Now, of course, in this instance, if we knew what A and B was, let's say that was 0 and 8, we could clearly say, oh, that's going to be 4, right? Because it's the average of those two x coordinates. Or you could go ahead and, like that last question, you could do negative b over 2a, sub it back into the equation and find that maximum point. That's literally what we're doing. Okay, so this is actually easier than most of the other things that we've been doing in this particular topic. As I said, not a whole lot. Now, this question here, I'm going to do very briefly. We've got find the maximum minimum value for the following quadratics or the corresponding values. Well, pretty clear in A, you can see it's going to be a minimum value because we have a concave up. We have that x squared, which means that the A is positive. So I'm going to write this A is greater than 0. Therefore, we have a positive function, right? And that's going to lead to a minimum value. Okay, like that, for example. Now, of course, you don't need to write this stuff down when you're doing a question. It's just something that I would like to address. The next one we hear, A is less than 0, because it's -2, which means we have a negative function, okay? Or it looks sad, which means we have a maximum value. So there are two things just to kind of get your head around so you know whether it's going to be a maximum minimum, because a lot of these questions, if you are asked to kind of show that it's a minimum or a maximum, that's what we're kind of trying to do at that point. Now, for part A, of course, it says to find the maximum value. Now, you could sketch these functions out, but we don't need to, and particularly with the first one, the product is 3, the sum is 1. So it's not going to come out nicely anyway if you want to find the intercept. So I may as well just go straight into using x equals negative b over 2a. That makes way more sense. So we get -1 over 2 times 1. So that's going to be my axis of symmetry. So what I'm going to do now is put that into my formula. Now, of course, be really careful, gents. We have a negative value here, so put your brackets around when you're squaring it, okay? And then it's a simple matter of getting into our calculator. So I'm just going to minimize this a little bit, gents, so you can see this on my screen. Okay, where's my calculator? I'm just going to use my old calculator, gents, so I apologize. Just it's a bit quicker to open up my calculator. So -0.5. So make sure you put those brackets in. So my computer is doing some funny things this morning. 0.5 brackets squared. We've got plus brackets -0.5. Don't really need to have brackets around that second one. And then -3. Okay, press equals. Okay, so we get y equals -3.25. So when it says to find the maximum minimum value, okay, we have a minimum or a global minimum of -3.25. And that, of course, occurs when x equals -0.5. Perfect. That's all we have to do for that question. Again, you get to kind of sketch a little function here. Okay, we've got a y value -3, and if that's -1, for example, that's the y-intercept, and it goes down just below that, something like this. Okay, you can kind of see how that parabola looks. Of course, I've got no scale there, so, but that's okay. Yeah, perfect. All right, next one. Just be careful with B. Now, B is no real different apart from having the -a value, but you can see that this has been, well, it's not in the normal format of ax squared plus bx plus c. So that's probably the only thing to kind of be wary of. Same thing here, x equals -b over 2 times a, which means we have -3 over -4, which means we have 3 over 4 as my answer. And again, to find my value, I'm going to plug it straight back into my equation, -2 brackets 0.75 squared plus 3 times 0.75 plus 3. And then it's a simple matter of chucking that into the calculator, okay, to get the answer. I'll do it very quickly, although you could probably do it faster than I can on the computer. 0.75. We've got plus 3 times 0.75, or 3/4. And those, of course, will be GCSE questions for us. Okay, we get approximate y equals 4.125 and job done. Now, they're just simply finding minimum and maximum points. They're not really applied to optimization, but they are finding the minimum maximum. So let's have a look at a question that you would probably see in exam, okay, or some type of this. Now, this is a really common sort of question. You might remember this from year 10, in fact, in the 5.3 course. A gardener has 40 metres of fencing to enclose a rectangular garden plot where one side is an existing brick wall. Suppose that 2 new equal side lengths are x metres long. Show that the area is enclosed by this amount. So often in optimization questions, you'll find that they want you in the first part to show you that you get a formula. Okay, you cannot use that formula in your answer. Okay, or to get your answer, should I say. It's very similar to what we're going through about our exam technique the other day. So we're given that in part A. So if we can't find it, we can at least go and do part B, right? But part A is where the money is going to be at. And it's the hardest part. And often in an exam, if you can't find it, don't spend too much time on it, but it is important. Okay, so we get this rectangle, you know, I'm going to put a y there if you want. We don't know what that value is. We've got another x on the top there. Now, think about what they've given us. They've given us 40 metres of fencing, which we refer to, I guess, as perimeter. In this case, perimeter equals 2x plus y. We know that the perimeter equals 40. So that's my very first thing. And they love questions, right, where they relate perimeter to area or vice versa. It might be area to volume. So you use the information they've got, because at the end of the day, what we're trying to show is the area of this rectangle. Now, of course, in this instance, I've got x, y, right? And in my actual question I'm trying to show, there is no y. So that means that we somehow need to take this y out and replace it, and probably with this 40 minus 2x. Now, of course, you need to show those steps. The perimeter working on the left-hand side here is where I'm showing those steps, because in order to get y on its own, on this little formula, I simply subtracted 2x and I get y equals 40 minus 2x. Now, hopefully what you can see is via substitution, area equals x times 40 minus 2x. I'm going to write here as required. Okay, in an exam, you're going to see AG, of course, it means answer given. So in this, like an exam situation, it's probably only be worth 1 mark in this case, because it's a pretty easy one. What they're looking for their marking, and I'm going to use a method mark here, they're looking for that part there, the method 1, that 40 equals 2x plus y. That's the perimeter. We're showing that we substitute into the formula, and then we get what they asked for. So that's the first part, and they can get quite challenging, gents. You've got to play around with those things. I might try and add a worksheet that has a lot of rearranging for you, and that might examine that part. Because once you get that part, the rest of it should be pretty easy. It says to find the dimensions of the garden of the maximum area. Well, we've got the formula A equals x brackets 40 minus 2x. I'm going to expand that. Now, I mean, yeah, you could do it like this. I think this is easy to do it. We make it 40x minus 2x squared. Now, we should know straight away that that's a maximum, because we have a negative parabola, which is going to get that maximum value. Now, I'm going to rearrange it again. A equals negative 2x squared plus 40x. Now, of course, you could do this a number of different ways, because it's going to be a nice factorization. You could find the intercepts and then find the midpoint, or you could simply use x equals minus b over 2a. And the fact is, we've got no plus c, but we don't really need a c value here in this case, because all we're doing is the axis of symmetry. X equals negative b over 2a. So negative 40 over 2 times negative 2. So negative 40 over positive, so negative 4, which means my axis of symmetry is 40 divided by 4, which is going to be 10. Okay. Now, if my axis of symmetry is 10, to get the actual value, area equals 10 brackets 40 minus 2 times 10. Area equals 10 times 40 minus 20 is 20. So area equals 20. Now, that 200, that's only if they asked you to find that value. And I'm looking at this and saying, well, they didn't actually ask us to find the value of the area, did they? They just wanted to find the dimensions of the area. So the dimensions of the area would be 10 meters, because that's the x value. Okay, and the y value is at 40 minus 10, 40 minus 20. And that's going to be 20. So my dimensions would actually be that 10 by 20, not the actual area. But they might ask you to find the maximum area, which is the area equal 200. But in this case, they just want the dimensions for that. So again, that came from the x value that you found and the y value by putting it back in. That's pretty much it. Gents, that is optimization. Okay, it doesn't get much harder than that, to be honest with you, apart from how you show or form these equations. I might add on an extra worksheet today to show you that. Apart from that, try and get the questions there. I think I've got some textbook questions underneath this. I'll just show you where they are. Exercise 2G, but I'll also try and put a worksheet that I used for my other year, my year 12 a little bit time ago. It has a lot about forming the actual equations. So once you've got the equations, it's really just x equals minus b over 2a and something back in. Have a wonderful day, gents, and hopefully I'll get to see you very, very shortly.